how do we find the distance between a point and a plane? Here we have our plane is in red and our point is in blue, and I want to know how far away, what's the shortest distance between the plane and the point, and I can visualize that with our orange vector here. So this orange vector starts on the plane, ends at the blue point, and its magnitude is going to be the answer here. This is indeed the shortest path between the plane and the point. So what is this orange vector? Can we just figure out what the orange vector is and take the magnitude? Well, the orange vector looks perpendicular to the plane, and in fact it is. For example, if I started on the plane somewhere else and I went to the point, I would be approaching from a diagonal. And that diagonal, here there's a blue vector that's approaching on a diagonal, is going to be longer than the orange vector. And so our intuition, or the visual that it looks like the orange vector is perpendicular, is correct. We have to approach on the direction of the normal vector, perpendicular from the plane, in order to get the smallest possible distance. Now, given the equation of a plane, we know how to find a normal vector here. And if I calculate my normal vector, well, there it is. Okay, that's not very helpful. See at the origin, there's the normal vector. If I read the equation of the plane, I get the normal vector is -2, -2, 1. I can multiply this vector by 5 just so we can see it, but that's a normal vector. However, I'm looking for the magnitude of a very specific normal vector, which is that orange vector. Remember, a normal vector to a plane just means you're perpendicular. It's not a condition on your magnitude. And so solving for this normal vector doesn't really help me find the magnitude of the orange vector here. What I want to do is I want to put the normal vector, well, at that gray point. But how do I find that gray point? This doesn't seem like an easy thing to find. If I was standing on the red plane, I could just stand underneath the blue point. If, up is that direction, that's kind of what I'm looking for. But there's not a very efficient way to find where the orange vector is supposed to start. So we can actually take a different approach here, which is, I don't really know where the orange vector is supposed to start, but it is easy to find just a random point on the plane. So here I've marked the point 664. It doesn't have to be 664. You could use any point on the plane. Maybe you're using 0, 0, -20. That's a completely legitimate point on the plane. And the idea here is, given a random point on the plane, I can certainly calculate how to get from that point to G, our point of interest, with a vector. Destination minus origin here, and I get what I'm going to call the vector B, because it's blue, B for blue. And this vector, as we said, is not the vector that I want. It's too long. But there's a way to figure out how much the blue vector points in the direction of the orange vector. And that will be the number that I'm looking for. The magnitude of the orange vector is what's called the scalar projection of B onto n. How much the blue vector points in the direction of the normal vector, called scalar projection, is the magnitude of the orange vector. And after a quick calculation here, we get that is going to be 34/3. Now there's one small technicality here, which is you may have gotten -34/3. Remember that magnitudes and distances are going to be positive, and so if you got -34/3, which is possible with the scalar projection formula, it depends on your choice of normal vector, you need to take the absolute value. Technically, the scalar projection is called a signed magnitude, and so you may have gotten -34/3, and you just need to realize, I'm solving for distance, this needs to be a positive number, I take the absolute value, and I'm good to go. The other thing you may be thinking is, wait a minute, I also saw there's just a formula for this. Can't I just plug in the formula and be done with this? Let's take a look at that formula and see where it comes from. It turns out that formula comes directly from the calculations that we just did. Looking at our formula here, we're going to just apply our scalar projection onto an arbitrary point and plane and see that we get the formula in the white box there. So first, let's look at our equation of a plane. So this could be any plane in question here. And then we'll have a point that we're measuring to, which is off the plane. And just like before, we're going to start with a point on the plane. So I'll call the point on the plane x1, y1, z1, and we'll calculate the same vector b that we had before. So our vector b is going to be destination minus origin. And this is our equation for b. And we can start to calculate the scalar projection of b onto n. And it will start to look like this. And when you calculate your dot product out and rearrange terms, we can see that the denominator is what we want, but the numerator isn't quite the formula that we're looking for. Where does this plus d come from? Well, let's look at our equation of the plane again and solve for d. If we solve for d, then we see that it's negative ax minus by minus cz. And I don't quite have that in my work on the right-hand side here, but what does that mean? When is that equation true? D equals negative x minus by minus c. Well, the equation of the plane, that's true for any x, y, and z that are on the plane. And specifically, our x1, y1, z1 is on the plane. So I can go back to my work here and replace negative ax1 minus by1 minus cz1 with positive d. It's a substitution I can make for any point on the plane. And this is why it didn't matter which point we picked on the plane. Our formula here, given in the top white box, or the scalar projection computed directly, will always give us the correct distance between the point and the plane, no matter what point you pick. And this is why, because this equation for d works for any point on the plane. And if I wanted to confirm that I get 34 over 3 in our example from before, there is our calculation here. We get 34 over 3. And more importantly, that is why the distance between a point and a plane formula works. Make sure to like and subscribe and let me know what you want to learn next.